Okay, so there is one other element I want to add to my model. So I will use the last example. So I think lately it becomes very popular for a presentation to include a map of Toronto somewhere. So I don't know for what reason, but I think it's kind of popular, so I included this as well. So this is a rental price map of Toronto. This example has nothing to do with the rental price, but as I said, I just included such that it's interesting. And so there are basically five locations. Suddenly there is a shock. There are five locations that are vacated, and five firms, or not five firms, a lot of firms are deciding whether to occupy them. So they start computing whether this location is good. I will assume that this location that is not really correlated. So these locations are the same, and any five of them would make the same. Locating anywhere would make the same profit, for example. So so at the beginning, so firm one at some point might want to choose to to be in Toronto, located in downtown Toronto. So that's his first choice. And firm two, then at some point after some time, firm two may decide to choose somewhere else. But that's not the complete game yet. But I will introduce the model first before I say something about why I have this example. So, so the model is basically the new thing you want to notice is that there is a small tau here, and this tau means so first a subscript is the order statistics, which means the tau smallest member of the set. So basically the idea is there are five different goods, so only the fastest five players get to implement their actions, or only the five fastest players get to locate in those five locations, which obtains some utility. So when tau is 1 is the minimum case. So the problem I want to say when introduce this is the same as the potential problem number 1. So I label potential problem number 2. It's that incorrect decision can flow from inferences about theta based on the first selection of a equals to 1. And this problem is called information cascade. I'll explain this using the third player. So by the way, this shouldn't be this slow. So when I program this, it's like 50 frames per second. So it should like blow up in 1 second. But it's kind of slow because the computation speed is slow, so it's kind of constrained. But anyways, so when firm 3 is deciding, he may receive a good signal. So if he is deciding himself, he may receive a good signal. He may receive a bad signal, which tells him not to do this. But the problem is seeing the first two guys deciding to act, then he's thinking there are two people who got this good signal. So even if I get a bad signal, if I use Bayesian inference, if I think all the signals are of the same precision, then after Bayesian inference it's 2 to 1. So there are two good signals, one bad signal. So then I may still want to decide to locate here. So similarly, firm 4, when firm 4 is deciding, then he sees three good signal, and even if he got a bad signal, it's only one bad signal. And similarly for firm 5, it's even worse. So it's possible that firm 3, 4, 5 all got a bad signal, and only two people get a good signal. So indeed, this place is bad. But I'm not saying Toronto is bad, but it's possible that this happens. But they have an information cascade, which means they coordinate on something that's kind of incorrect. So again, the way I solve this problem is introducing this order statistics. So people actually, when they decide, they don't actually know that the other person choose one at any point. So we basically, all five people keep deciding until I finish my decision. and I submit whether I say 0 or 1. And then if I'm the fastest, I got the good thing, basically. So I will assume that people do not observe other people even choosing action 1. So the two potential problems are problems that are interesting and it's relevant in real life, but my model excluded. So what I'm saying is, if I have time, which I will, I I will try to incorporate those ideas as well into this model after I solve the basic model. But I will probably do that next September. So now the summary. So there are some partial results which A can be solved exclusively. So you basically have an estimate. So each one, so the idea here is each one will have an estimate of this theta hat. Theta hat is 0. If according to my estimate, it's greater than 0, my utility, then I buy this. So this is the obvious part. So the other part is we can introduce a value of a model. And this value of the model is the negative of the loss of this model. And the loss is computed by this. So if my model prediction, which is this thing, and the actual value has negative sign, it means they reach different decisions. So I either bought something that's not right, or I didn't buy something that I should. So there is a loss is g of theta 0. So I take the expectation over all the thetas. Then I can find this value. And if I maximize this value function for each time constraint t, I can I can subject to a constraint such that the model size is a certain number, and then I can do this. Of course, if it's the multiplayer game, I can do some thing that's similar. I can calculate the expectation given a model of size t. So but however, I think there is some problem with this best response function because I for some reason, I don't really know. I assumed U is decreasing, which is not necessarily true. So one of the other best response functions could be, it's also possible for the best response function of t to be t plus 1 as well. So I kind of ignore that. So I should add that. But in any case, a Nash equilibrium is basically a optimal t such that it satisfies some condition. I think the condition here is not right. We need it to be greater than ut plus 1 as well. But there would exist some t, that t may be 0, such that people would coordinate on a model of a particular size. That size such that we don't have incentive to deviate to either to increase the complexity or decrease the complexity. So some of the conjectures or why I'm asking the question here. So the first is under what conditions of the parameters will the players converge to a particular fixed size model. So the economic question to ask is, will the rational player choose to coordinate on some simplified model S star? Is it possible that some players completely randomize, which means the first case, there's no model, I just always need the same decision, or build some model that's infinitely complex, which is the last one, the size is converging to 0. I mean, converging to infinity. So in particular, the two questions I want to confirm, I want to show under what conditions will the slower player use a simplified model. So for example, with high frequency traders, well, human traders just completely randomize because the computer traders are too fast. So I have no reason to think about anything. I just randomly add, which actually this is consistent with the something called the no arbitrage principle, or the one fund theory, which means people can basically randomize their their investment choice. The other question I want to ask is, well, a decrease in C. So, well, a decrease in the cost of building models increase the equilibrium model complexity. So suppose there is an equilibrium model complexity. So basically an idea, for example, is after the second years of papers are published, well, that home buyer who thinks about a lot of things, you use those information because the cost of setting the models themselves are decreased, so the wording is very bad. So in the next 6 months, of course, like everyone else, I need to work harder and hardest. I forgot to have the time constraint. So in the first 2 months, I'll probably just sit there, and then for the last 2 months, I'll be going crazy. Of course, that was just joking. And so I'm trying to solve some specific example first. As you have seen before, the result is probably too complex. There is no explicit form result of any sort that I can deal with. So I need some specific examples. So in the middle 2 months, I will try to solve more general cases to see how much I can get as far as possible. I will also try to incorporate the two potential problems that I mentioned, which means I need to change this model somehow. And at the end, I will try to write down. I will not try to. I will write down the paper. So, of course, there's no conclusion yet. I would like to thank Professor Marshall Cassidy for providing many ideas and suggestions, and also attending this presentation. And also, I would like to thank Professor Carolyn Dietrich for comments on the presentation slides and content. So that's all. Thank you.